Thank you very much. It's great to be here with you all. Yes, so my name is Jay. I wrote this book with my co-author, Hands-on Large Language Models. We'll be doing, I got 6 copies from Amazon myself that we'll be giving away tomorrow at lunch. So we couldn't arrange for the publisher to send things in time because of my travel logistics. But if you're around tomorrow at lunch, we have very few copies, or if you have already purchased copies, happy to sign them. I've worked for 4 years now at a company called Cohere that builds, it's one of the earliest companies that builds large language models. And I've been doing that to sort of learn and see how that technology goes out from the lab and into the industry and into the economy. And for the last 10 years, I've been writing this blog where I visualize and illustrate some of the most important, or that I find fascinating, ideas in machine learning in the beginning, and then NLP, and then large language models. And so in that, in writing the book and in the blog, we had to sort of, the role that I play in this community is to understand topics and then try to find the easiest way to sort of communicate them to people visually. And so here I'm going to be sharing a bunch of that. PyData London is my absolute favorite event, and I go to so many. I spoke at 18 different conferences from academic to industry just last year. PyData London is extremely special to me because in 2018, it was my first time coming to an event like this, and I saw talks like this by Gail, who is the, is the maintainer or one of the creators of scikit-learn. And to me, people who create incredible open source software like this are superhuman. Like it felt surreal. I was in awe walking through the halls of that venue and seeing, oh, this is the one of the contributors to Pandas, and this is the creator of scikit-learn. These are people that not only have created incredible software that I used to learn a lot of these, but they also gave it away for free, and you can use it and you can download it. Spacey is here, love Spacey, and there's so many of these software projects, and this is maybe one of the most communities where you can see a lot of that power and a lot of those people for that community, which is quite important. I go around and talk a lot at conferences, and this is a slide that I use to demonstrate large language models. And I say, about 5,000 years ago, we had the invention of writing. That was a pretty big innovation in technology. Like, you can think about writing as a technology, and that has changed the trajectory of this species and of this planet. About 400 years ago, we invented the printing press. Before that, you couldn't print books. You had to go copy them by hand. And so in just a few hundred years, we have what we have right now, because these two tremendous technologies came. And I've always wondered if we're living through something like that with AI and NLP and language models. Are we in something that can be as big or as transformative as these technologies? And when you look at the industry over the last 10, 15 years, there are jumps from the internet to the personal computer to the smartphone that change so many things. They change jobs, they change possible business models, and they do it very, very fast. 5 years ago, this is maybe one reasonable way to point at the birth of prompt engineering. This is when we sort of started to say, okay, we can shape lots of problems as language problems and use these transformer decoder or encoder-decoder models to solve these problems. One just example is the T5 paper, and I love this figure because it just shows how you can solve different things, different kinds of problems using one model. This is a random plot from a CSV file that is stored on scikit-learn. And this plot was made with pandas and matplotlib, but I did not plot it myself. I presented a prompt to one of these AI agents that you see out there. This one is called Manus, but there are so many that can do this type of thing. And I said, give me a line chart for the closing prices in this chart. And from there, you have this AI agent going around using tools. So it's using a browser, and you can see its browser window there of what it's looking at. It spends quite a bit of time sort of trying to read this, so I can skip through. So it's viewing the browser. It loads up some bash, writes some bash code to sort of, it downloads that file. So it has access to some sort of a VM. So it downloads the file and runs the bash command to look at that file. It writes pandas code, matplotlib code. It runs that and generates it. So if you're one of the authors of some of these libraries, this is going to be a big set of your users coming up. And then it goes on in multiple steps. It has one plot, and then it wants to improve on it, and so it gives this other plot, and then that's what happens sort of in the end. So this is a massive jump, it feels like to me. Like I keep being surprised by how fast this is going. And if we put that in just a quick timeline from these jumps, a lot of this just happened in the last 5 years, 8 years, of having systems that are able to do this. We're no longer talking about a single LLM. An agent is not a language model. It is powered by a language model, but it's an amalgamation of software around that does things in a very surprising way, it feels like. And this is what the majority of the talk is going to be, of how did we get here? What is the state? What are the technologies? What are the training processes that enabled us to make this jump over the last few years in sort of these categories of the training processes, the models that we're sort of using currently, and then closing by a little bit of talking about beyond. So this is the general recipe of how language models are created. You start with an untrained, randomly initialized model. You do language modeling, predict the next word. You create what's called a base model. Then there are steps of fine-tuning to improve it, and then there's variation of applying these steps in the order of them from supervised fine-tuning and reinforcement learning fine-tuning. A lot of new paradigms now, the idea is called the first part pre-training and that other part post-training. And it's kind of funny, where is training? There's no training, it's only pre and post. So pre-training is language modeling, and language modeling is this NLP, long-running NLP task of predict the next word. You extract training examples from newspapers or from web text, and you show the model 2 words, and you hold the third word, and then it will make a wrong prediction. You update, you do your back prop, and you update its weight, so it has a better chance of predicting it in the future. Supervised fine-tuning is giving the model examples. So who in here has used GPT-3 as a model? So we have a good maybe 30% or 40%. This is what GPT-3 was. It was only pre-trained. And to get it to do anything useful, you had to do very complex prompt engineering. It was able to do a lot of these things, but the prompt engineering is difficult. So to improve usability, instruction tuning in SFT was one of the first things that were added just to make the models more user-friendly. And that is done by training the model on examples like this. So if I ask you a question, don't answer by giving me a list of other questions that are similar to it. No, if I give you a question, give me an answer. If I give you an instruction, follow that instruction. If I tell you to write an article about something, follow it. And that's how instruction tuning sort of started. And then one way to improve the output and behavior of these models, this idea of preference tuning or using reinforcement learning from human feedback as one of the algorithms it came by. And one way to do that is to have one prompt, you present it to the model to get 2 different generations, and then you have a human labeler that sort of chooses which one is better. Is it A or B? And you needed reinforcement learning here because that vote of preference, if it's a human, you cannot backprop through the human. So you're not able to use the same methods that you use for pre-training in this step. So that's where reinforcement learning started to happen. And then human labelers are very expensive. So there was a lot of work on how do we automate this annotation process, and where this preference evaluator no longer needs to be human. There should be humans there, but how can we automate it and get more sort of data, more systems that are able to do this, so we can get a larger scale to do that. That was the advent of reward models, and reward models are an important piece of the recipe. And a reward model is a language model, except you chop off the last bit of it. So instead of predicting the next token, you give it a classification head. So this is one way of creating reward models that automate this preference labeling of these systems. You create them by training on preference data that looks like this. So a single example is you have a prompt and 2 generations. So you say this is an accepted generation and this is a rejected one. It's not necessarily good or bad. Both can be good or both can be bad, but this is better than that. And then the training process of a reward model is kind of like this. You have it assign a score to each of the examples. And you can look, this is, for example, what the Llama 2 paper has. That's the DPO sort of objective that enforces that learning objective is to enforce that this, you have a better score for the higher, for the preferred or the accepted one, and a lesser score for the rejected one. Let's see what I do. Okay. Yep. Let's see. If we get the video again. Okay. And so now we have a reward model that is able to assign scores to, and that's one of the most important components for doing this. One of the biggest changes in the last 8 months, and that really changes how people think, how fast these models can go, or how fast human-level AI can come, is this rise in reasoning model that happened. A lot of these models started coming around last maybe November or so. I have this post on DeepSeek R1 and how it was sort of created. And just to give you a sense of how this jump in reasoning capability or model capability came by, DeepSeek R1 breaks this generation problem into a thinking step and then an answer step. It is trained using the same ideas, so it's SFT, supervised fine-tuning, and then reinforcement learning, but it's done in slightly different ways. So for a model to be really good at reasoning, it needs to see reasoning data, and it needs to train on them. But those are very hard to find in the real world and extremely expensive to train. So reasoning traces are going to be multiple steps with thoughts, kind of like the one we saw in the example that the model and the agent was doing. And so to do that, they trained an interim reasoning model that is able to do that. And it seems like a catch-22. If we're not able to get these, how do we do that? And they demonstrated how they got a lot of these reasoning traces by using reinforcement learning alone on a base trained model. So in their paper, there's this sub-model called DeepSeek R10 that was trained without an SFT step. So they took DeepSeek v3, a base model, just applied massive reinforcement learning to it, and from there, the reasoning ability came forward. And that was a striking development, that you can get that with reasoning alone. And the process there is you have a question. So one thing that makes this possible is reasoning problems tend to be either mathematical problems that have a gold answer, or code problems where you can verify automatically using things like unit tests. And so that's where you can get a lot of the additional capability on reasoning models. And so if we have a training example kind of like this, where we say write Python code that takes a list of numbers, returns them in a sorted order, but also adds 42 at the start, you can sample for generations for possible answers from the model for that. And some of them are going to be wrong. Some of them might be more right than others. But you're able to sort of automatically verify that. And so with automated verifiers that are in software, we're able to grade this. And you can see that this is also training signal that is synthetically generated or automated, created by software. And so if we have these 4 examples, we can say that the first one is not code. any linter can do that, or Python. You can run it. Is it Python or not? And then does it pass the unit tests or not? And a lot of the times, the training examples don't even need to come with unit tests. The previous generation of code generation models are really good at generating unit tests. And so you start to see these models building on top of the capability of the previous model. And these are some of the things that are continuing to push this. And so you have the solution scores based on the unit test, based on your verifiers, and then you update your model based on those to increase the likelihood of the correct ones and decrease the likelihood of the wrong ones. And that's sort of how you get models to write code. But this is a single step of code generation. This is going to create a model that is good at lead code problem. This is out of distribution. If you're doing 7 or 8, 9 steps, how do you do that? So model creators and LLM trainers have to train on these longer trajectories. And so what's done here is that you have this prompt, like the one we saw in the earlier video. You give it to the language model, but this language model knows that it has access to a bunch of tools. So we saw it being able to not only write Python, but execute that Python and sort of work on whatever comes after it. So you give it a tool that is a Python interpreter. We saw that it was able to browse and sort of open a web browser and look at the web and download information from the web. So that's another tool that you give it. And then you can also give it access to some Docker environment with Bash, so it's able to run commands and do that. And we saw it use all of these. But that has to be, to improve how these models work, this has to be seen in the training phase. And so the model does a step-by-step, let's say, execution of these various steps. And so we give it this problem. It says, OK, I'll call the bash tool, and I'll give it this command, for example. And then I'll call it again, and I'll give it this other command. And then I'll call the web browser, and I'll give it this URL address, so it goes in and fetches it. And then I'll write some code. I'll send that to the Python interpreter to change my environment in a certain way. And then that plot I didn't like. Let me add that sort of trend line to it, for example. That's another Python call. And so that now you're building something that's multiple steps, and that's how you get this final figure there that the model figured out how to create. Now, some new lingo and some vocabulary that is going to be more and more important as the agents sort of start becoming more a part of what we do in data science is that this is a trajectory. A trajectory is a certain number of steps to solve a problem. And to solve it, the model has to do, in the training process, we do these rollouts. So you have the model try to solve this problem multiple times, and you get these rollouts. And some of them are going to be successful. Some of them are going to fail through errors. And some of them are going to fail through your verifiers at the end. They will give you an output, but is it correct or not? The Sutton and Bartow book on reinforcement learning is one of the best sort of resources that explain reinforcement learning in general. It's a little difficult for me. I'm not that smart. I need a few more people to sort of explain these in more accessible ways, because once you get in there, yeah, models are not models anymore. Models become policies, and let's not talk about it. But it's incredible work. They won the Turing Award for a lot of the research that they've done in reinforcement learning. Now, one thing to think about here is as models started becoming able to do these, benchmarks have also evolved to measure these capabilities. The agentic capabilities of models solving problems using tools across multiple steps. And while 2 or 3 years ago, the top LLM coding benchmarks were like lead code problems of sort this array or traverse this tree, now you start to see things like SWE-bench, SWE bench, software engineering benchmark, which is, if you see all the latest model releases, that's one of the things that all the models, the LLM creators try to compete on. And that's a problem where you give the model a single GitHub issue link, and then it has to solve that issue. And you can see how complex that is, because to do that, the model has to have access to a Docker environment. It will go and clone the repo. It will try to replicate the error. It will read the README and the discussion to try to locate where the files that can lead to this problem are. It will try to solve it, and it will then try to run the unit tests that existed prior. It might write new unit tests that show this figure. So this is a very difficult problem. I have a video that I uploaded on the blog where I interviewed at NeurIPS the creators of this benchmark. And I asked them if they thought it would be saturated by the end of 2025. And they didn't think so. It was very difficult. Like, for a year, it stood at like 4% or 5%. 2 days later, O1 came out, and it reached like 60% or something. And now you can see models that are at 70% or something ridiculous like that. So this is becoming, let's say, advancing very quickly. And it happens in data science as well. If you look at a data set like DA code, it's agentic, kind of like this, but it applies, the multiple steps are Python and pandas and matplotlib. And so reinforcement learning happens at 2 times, let's say, in creating DeepSeek R1, or the latest LLMs. One during the SFT stage to create these traces of reasoning data, and one towards the end. And then the step towards the end of applying reinforcement learning is not just to create the reasoning prompts, which the first step is only focused on reasoning. But that gives you a model that is only good at reasoning. If you have to ask it questions to do RAG or to do tool use or to do other things, it doesn't do so well. So to improve the general behavior, there's this general prompts training step that happens at the second step. And there you use other reward models for safety, for helpfulness, to improve the model's behavior on non-reasoning problems. So this was maybe the state of the art as up to maybe December. And then you see similar things with the more recent models. So this is Qwen 3. And you can see there's a reasoning and creating the cold start long chain of thought reasoning traces. And then you can create smaller models by distillation. One thing that is also a little bit mystifying is you hear a lot of this. The internet there's so much AI slop, and that training models on that is not good because a lot of it is blog spam, for example, and the models will deteriorate if that's what you train them mostly on. But actually, carefully created synthetic data is also one of the major things that are making these models better now. And this was a major shifting point in maybe 2024, where Llama 2, its post-training data was mostly human annotated, and then Llama 3, most of its post-training was from Llama 2. So the models have become so much better at doing these that even it's gone to base training, and you see it in, like we saw it in RL, it's rollout and verification, so that's synthetic. And then a lot of the SFT is also synthetic now if you have the right recipe to create it. And code lends itself nicely to that. You can run the code to execute it and see, do you get the output? You can have a unit test and you can have other things. The Qwen 3 paper says that their base training, the language modeling step, was run on 36 trillion tokens, and a lot of that is synthetically generated. That's a staggering amount. And there isn't maybe enough data that is clean out there, but the models, now we can see this new modality of creating training data. In Cohere, we've worked on one tool in the toolbox of model creators called model merging. And this is the idea that you can have 2 teams work on different specialties for the model. And then you can merge the weights of these 2 models, and then you get the best of both worlds. You get very close performance on the tasks that you want to create by that merged model. That merging can be basically averaging the weights or the parameters in the feed-forward neural network, for example. This is the post-training recipe for a model like Command A, where you can see it's mostly SFT here, but the supervised fine-tuning happens across different capabilities. So multilinguality, RAG and tool use, you have a team working on that to be really good at that, creating and labeling data that does that. Code and code generation would have its own maybe team and creating a code expert, math and reasoning, long context, safety, instruction following. And then you can merge these, and you can have these weighted merges where which capabilities do you want to sort of draw forth and which ones. And a lot of modern language model ops or operations are about, if we want to improve this capability, how much does the other capability sort of regress, and how do we find sort of ways to balance them? And this happens across sort of multiple steps. It happens in the reinforcement learning, and then you have another merge there, and then there's a polishing step where you take it through multiple stages of reinforcement learning and preference tuning to get the behaviors that you want. So we have a 40-page technical report with all of these details. Please check it out. Let's see. So we can go quickly through the models. Language models, you give them a prompt, they break them down into tokens, and the tokens are translated into embeddings, and that's where the model, which is a language calculator, calculates. You can see these tools that show you a little bit of how the tokenizers work and how they break down the letters. Models have never seen a single word. They only see these token IDs, which is a little bit surprising. They can write the best Shakespeare-like without ever, really seeing a word. They just see token IDs. And I have an example in the book showing if you have a string like this, how do different tokenizers break it down? And you can see BERT models, for example, take away the new line characters. They take away emoji and foreign non-English scripts, for example. All of that becomes invisible to the model. And then models do funny things with numbers and how they represent numbers. Some of the better later models started to really pay attention to tokens, maybe splitting them, doing more interesting things. But if you want a model to be good at code, you need to pay attention to how the model tokenizes code or numbers. So the modern transformer large language model generates tokens one at a time, kind of like this. It does that by passing its input through 3 major components. You have your tokenizer, you have a stack of transformer blocks. This is the neural network where everything happens. And then you have a small step in the end to choose the final output based on all that processing called the language modeling head. The tokenizer knows a certain number of words. Maybe it has what's called a vocabulary. So it has maybe 50,000 tokens that it was trained on. And with each of these tokens, there's an embedding that is stored in the model that is a representation. It's a numeric representation. It's a list of numbers, a vector that represents that token, and this emerges from the training process. At the output, what finally happens is a score, is a probability score of each of the tokens that the model knows. So that's what happens at the end of the neural network, and then you can pick the top one, and that's what happens at temperature 0. It's just no probability, just pick this one. Or you can have a probabilistic sort of way to say, consider the tokens that are at the top 90% of the probability mass, and maybe sample them based on that. So that's what you control when you tune the temperature knob, and these are the various decoding strategies that models are able to work with. Current LLMs are mostly decoder-based. That's a little bit different from the initial transformer that was an encoder-decoder model. They work kind of this way. You can think about, you hear about context size. You think about the context as a number of tracks flowing through the model. And then the input tokens flow each in its own track all the way through block 1, and then block 2, and then block 3. When you're generating text, the last track that you're looking at, the token that comes from processing the last token is the generated token. And then once you're generating the next token, you don't need to process everything that happened before. So a lot of the performance, a lot of the things that improve the performance of current transformers is you don't need to, you can cache all of the results of the previous steps. And so in the next step, you're only processing this one flow, this one track flowing through the transformer. This first stage is sometimes called the pre-fill stage. And then here you have the processing. To understand a little bit of just high-level overview of the transformer block is you have your embeddings, raw embeddings, or static embeddings in the start. There's this film, The Shawshank Redemption. It's the only time I hear this word in the English language, and so we'll use it as an example here. The transformer block has two components, and to oversimplify it, the feed-forward neural network is able, if you give it the Shawshank, it's able to just statistically tell you that the word redemption is the one that tends to come after the Shawshank in the data sets that this model was trained on. And so the feed-forward neural network sort of stores a lot of this statistical information. It's able to predict sort of the next word. It does that by, it usually looks like this, so it expands the network to a larger size. Usually if you have, let's say, embeddings of 512, usually model designers multiply that by 4, and that's the dimension, the hidden dimension of the feed-forward neural network layer. Self-attention gives the model the ability to understand the context. So if you have an example like the dog chased the llama because the model cannot understand the word it without sort of knowing, does it refer to the llama or to the dog? Maybe previous text in the input points out or helps sort of point out what that is. But that is what the self-attention layer does. And to break it down into sort of its most simple way of understanding it, say you have 5 tokens, self-attention step, which is what the transformer was named after. So the paper was attention is all you need. It's just about describing this process. And it says, how do you pull in the information from the previous tokens to this one that you're processing so that you make the best prediction? And this is not only for language processing. When you think about prompt engineering and the system prompt and the developer prompt that you need to do, all of that factors here. So this sort of pulls a lot of that information and the decision-making process for model behavior. It does it by 2 steps. There's a relevance scoring step of, okay, I know this the current token, I know the previous ones, let me score all of them, and then combining information step. So based on the relevance scores, it merges them as a weighted sum. And we'll not go exactly into, so in general, you just need to know that there's 3 matrices, the keys, queries, and values, that are, their interaction is how the model does these 2 steps. This happens across attention heads. And so each attention head has its own set of these. The biggest developments on the architecture side is that a lot of the compression here. So all of the attention heads now started sharing things like keys and values. So this is what's called multi-query attention. But this turned out to be too much of a compression for this. And so the next development, which is you currently see in the current crop of LLMs, is this grouped query attention, where you have maybe 3 or 4 groups. Each group of attention heads share key and value matrices. So this is a knob for the model creators to sort of control how this model is created. Now, that was a just high-level overview. I hope that now, even if you're not an LLM expert, if you can come across a paper like the Llama 3 paper, and you see the architecture description of the architecture of this paper, that you have a sense of everything that happens here. The layers are the number of transformer blocks that we touched on. The model dimension is the dimension or how many numbers are in this figure. The feed-forward neural network dimension is how wide it gets in that neural network. The attention heads we covered, the key value heads and groups we touched on, and vocabulary size. So now you sort of are an LLM architect, and that you sort of know all of these figures and what they mean. So this was the transformer block of 2017. It has something called positional encoding. That is no longer available in current, or it doesn't happen in this step. It happened because of reasons like this. So when you want to train models, you need to pack that data into batches. And if you have short documents and you want to train a model on, let's say, context size 8,000, and even models that end up at 1 million tokens, they start by being trained on a shorter context length, and then that is sort of expanded in certain stages. But if you have a document that is, for example, a single tweet, you don't want that to be just a single example in the training batch of 8,000 tokens, and just give it a lot of padding. That is inefficient use of training. And so what actually happens is this. So you pack a lot of documents with separators between them to indicate that this is document 1, this is document 2, and there's a separation between them. And then doing this forced, let's say, or raised the need to have positional encoding mechanisms that say that token 1 in document 2 is different from token 1 in document 1. Because when the model is operating on each of these documents, everything else that is not part of this document should be masked. And so that's where you see things like rotary embeddings, which is the positional encoding method that is used in most of the current models. And this happens at the self-attention layer now. It doesn't happen in the beginning. It happens at every self-attention layer. And so this was the original transformer 8 years ago. This is the famous figure. We talked about the language modeling head, but it does. We saw decoder transformers very closely. Encoders sort of are quite similar to that, and that's how they break down. So now this is the modern day transformer. Looks very close, but just a few things have changed. The order of the normalization happening before the steps, the type of attention, now we have grouped query attention and rotary embeddings, and the type of normalization. One major thing that you start to see is this idea of mixture of experts, which is a very confusing name for people. But the basic idea there is that these are sub-blocks, sub-neural networks in the feed-forward neural network. One of the best guides to that is my co-author's blog post, a visual guide to mixture of experts. That's where I'm sorting some of these. So people, it's easy when you hear the name that you assume that this is a mixture of experts model will have a psychology expert and a physics expert, and that's not it at all. So what you do have is sub-neural networks as a part of each layer. And a router sort of decides which expert. A router is also a small neural network at the beginning of each layer that decides which of these experts is the one that is sort of encoding the next one. And if the router of layer 1 decides that this is expert 1's token to process, in layer 2, this might also be routed to number 3, or so it doesn't stick to, let's say, one stream of experts. This is another way of looking. So we saw how the feed-forward neural network is just one dense block in non-mixture of experts. In mixture of experts, that is just broken down like this. So you have a lot more networks in parallel. Some of them will be active, but most will not be active. And this gives models more representational capacity, so they can store a lot more, let's say, maybe specialized information. Models like DeepSeek R1 merge the two. So the first 3 layers are not mixture of expert layers. They're transformer blocks, dense blocks like we've seen. But then from block forward onwards, these are mixture of experts. And the processing sort of flows through sequentially, kind of like this. Some of the more recent developments is that in R1, multiple experts are activated. So that's another hyperparameter for these models. So it activates 8 experts that process this from 256 that are optional. But then there's this idea of shared experts that are always on. So this, let's say, a hybridization of the types of experts between dense and. So this was, a quick look at these models and a quick look at how we got from here to here, from LLMs being systems that answer questions. They take text in and give you text out, to them being able to solve problems at the level of the GitHub issue, using tools across multiple steps, and with that solve more complex problems. Now, so this was I don't know if anybody sort of expected how fast this will transpire and what is to come next. I got to see Richard Sutton, the RL author of that book earlier, and he was talking about beyond. He broke down, let's say, human history into these 2 phases or 3 phases, and gave them different names, where he was saying, sorry, we're going to take a photo of that. So he was saying that we can assign different names based on the technologies that we have for these eras. This is one slide from a presentation that he's done. He's presented this slide too at the conference that I had gone through. This is Upper Bound, just earlier this month, I believe. And so he says a lot of people say that we would break this down into the age of humans and the age of machines, and that is not the most accurate or precise way to describe it. And he was giving these names of age of replicators and the age of design, where written language sort of separated those 2 phases. And so that is one thing that is useful to think about as we go forward, and how things can transpire. As people think about these new capabilities, they can definitely see ways of it heading towards utopia or towards dystopia. And we all individually think about this, I think, a lot of us. And as communities, we also sort of need to think through these. I really love this interview with David Brin, a sci-fi author. He's one of the most prominent sci-fi authors. He shares a lot of thoughts about the future of AI. One of them is that, who in here has seen Dr. Strangelove? Okay, I have a good 50%. So he's saying that science fiction and things like Dr. Strangelove are, with a high probability, one reason why we are alive now. Because he's sure, and he was told, that generals that design nuclear systems have seen this film. And this film sort of has this dramatization of the destruction of the world because there was a system that's a nuclear deterrent system that was triggered automatically by some bug, and people weren't able to sort of fix it back. So what Brin was saying is that this is one example of how thinking about the future can really help people design the future, and that's one reason why we are currently alive. This biggest, let's say, shift, I think one of the strongest forces that are pushing us forward and to where we got with LLMs here, the open source software, which we as a group are some of the best representation of, held together in one place, is one of the most major forces that are doing that. That's a little bit of why, I was in awe of these people who create these open source software and the organizations that sort of support them. So I tweeted that scikit-learn has created billions of dollars of value. It doesn't capture a lot of it, but it definitely has. And a lot of these models are built on software, open source software. It's all on Unix and Linux and scikit-learn. We saw how it uses pandas there as well. And so, yes, as individuals, we have power, but as groups, we have incredible power as well. And one of the best examples that I think the future of humanity has for examples of working together and playing non-zero-sum games is the open source software movement of people doing incredible work and sharing it openly, sharing the knowledge, sharing the code, sharing the documentation. And these are some of the best examples of that. And that's, it inspires awe in me, and I find I get a lot of inspiration. That's why I try to come to PyData London to get more of that inspiration and sort of work with all of you. So as we've pushed human development for the last few years, hopefully we can push the trajectory from one side to another. Please donate to NumFOCUS, and thank you very much.